Yesterday we started 1.2 notes, and today we are going to continue and finish the notes today. Yesterday we finished off doing B3, which was converting our seconds into minutes, which we know now that 60 seconds is in 1 minute. So when we do those conversions from yesterday, we were doing like 60 times 1, just a little review from yesterday. We did stuff like that. Well, now I will let you know that for B3, it says, what is the walking rate per minute, which is what we just did over here. That's what we finished off with yesterday. And then it says the walking rate per hour, which that's what we're going to start with. The walking rate per hour. A little refresher. What is Elena's walking rate? Eliana. It was 1. That's right. So I will let you know. That was 1, what did it say? 1 meter per second. Now we want it in hours. So in hours, there are 3,600 seconds in 1 hour. 3,600 seconds equals 1 hour. I'll tell you that conversion right there. So now that I gave you that type of conversion, we can figure out what Elena Gilberto's and Leanne's per hour, meters per hour is going to be, right? Yes. Okay. Yeah, you went from seconds to minutes, and then you did your minutes and converted your minutes into your hours. You can do that if you want. That's doing like a 2-step type of thing. This is just doing 1 step. We're converting right from seconds, and we're skipping that minute step that you did, and we're going right to our hours. If you want to do that, that's fine. Like I said, this is just skipping a step, so there's less space for us to make mistakes if we happen to, okay? So let's do it this way for today, though. So Eliana told us that Elena has 1 hour, or I'm sorry, 1 meter per second. So to figure out what that is in hours, we would simply just multiply that by how many seconds are in an hour. So, Elena, what would that be then? Yep. When we multiply it by 1, it's just 3,600 still, because it's just being multiplied by 1. So if we were to go on Gilberto, his walking rate, Gracie? Yeah, his walking rate per seconds. Yes. Was 2. Exactly. So if we want to find it per hour, Gracie, how am I going to do that? Perfect. 2 times 3,600 to get it in those hours. And when I do that, Aiden, do you have a calculator? Who has a calculator? Who wants to calculate it for us? Brayden, you want to? 7,200? Perfect. 7,200 is Gilberto's per hour, meters per hour. And then lastly, if we go on to Leanne. Anthony Coleman. Leanne, what was her walking rate again? Let's do a little refresher from yesterday since we went over it yesterday. 2.5. Okay.
Now be times 3,600.
Times 3,600 equals 9,000 exactly. Perfect. So that would be her meters per hour. Blake, did you have a question? Okay. Okay, so if we go on to part C, our last page, it says sorry, let me grab this. 4 other friends who are part of the walkathon made the following representations of their data. These are 4 different friends now. Could any of these relationships be a linear relationship? How can we, based on what we went over yesterday, let's kind of review a little bit, how can we determine, looking at a table, if it is going to be a linear relationship, which means it is a linear equation? We can make a linear line in a graph. Elena? If it increases by the same number, so it's going to go up by that same amount, which means what is that really representing when it's increasing by the same amount? Constant rate, which is our slope, right? Yeah. So let's look at that right here. Let's start with George. Can someone tell me, Maria, What's George, his distance going up by? Right here, 0 to 2 is what? Okay, perfect. And then 2 to 9? Oh, 7. Yep, you're right, 7. 7. Okay, and then 9 to 11? 2. 11 to 20? 9. 20 to 5? 25? 5. And now let's just look at the left side. It goes up by 0 to 1. That's 1. 1. Okay, those are going up by 1s, right? So we have 1 to 2. Second column, we have 1 to 7. We have 1 to 2, 1 to 9, 1 to 5. Based off of what Elena said, is that right-hand side, that distance has to go up by the same amount each time. Well, Maria, based on that information that we know for a linear line, could this be represented as a linear line? No. So we would write just a big NO next to it to say, no, this cannot be a linear representation. And we just showed why, because 2, 7, 2, 9, and 5. So showing that tells us that it is not a consistent rate. So if we go on to Elizabeth, let's look at her distance, that rate there. Joey. 0 to 3. 3. 3 to 6. 3. 6 to 9. 3. 9 to 12. 3. 12 to 15. Okay. And now let's just quickly go to the left side too. 0 to 2. The time part. 2. Okay, 2 to 4. Okay. 4 to 6. 6 to 8. And then 8 to 10. Perfect. Thank you. So, Joey, tell me, is that left-hand side, the times per seconds, in seconds, is that a consistent change? It's going up by 2s. You're right. What about that distance? It's the same also. So back to what Elena first told us, is that it's a consistent change. So Joey, would you think this is yes or no? Can this be represented as a linear relationship? Yeah, it could. Because that 3 is really telling us what our slope would be if we were to create an equation. That would be our mx. It would be 3x there. That's what that would represent for us. Over here, we didn't have an exact slope because it was different each time. So if we go on to Billy, Isabel, you just came in. Let's do Becky. Let's look at Billy. Billy's walking rate is d equals 2.25t. This is given to us a little different. George and Elizabeth were both represented in tables. Well, now we don't have a table, but they gave us an equation, which is completely fine, right, Becky? Yeah. So, based on what the equation of a linear line is, can we determine if this is written as a linear line equation? Yes. Do you remember what that equation is? What it should be shown as? Y equals, I'll give you that first. We kind of, let me see, I think we went over it yesterday a little bit. Didn't we write it out? Yeah, we did in question 4 on that very first page of 1.2. Each equation is y equals, do you have that written down on your page? Yeah, number 4 in the very front. No? Okay, that's okay. So let's go back. When we have a linear line, we need a slope, right? So what's a slope represented as? What variable? We have y equals, and our slope is m, right? And then there's always that x connected to it. And then we need a y-intercept, which we represent as plus b. So that's a slope-intercept form. That's how we express it. If we have this type of equation, we can always put it in a graph. We have our m, which is our slope, and we have our b, which is where it's crossing that y-axis. Sometimes we don't have a b, and that's completely fine. As long as we have that slope to tell us how to plot it, we can do it. So now that we know that, Becky, can we look at Billy's walking rate to determine whether it is in that type of form also? Yeah. So that d in his form is really the what in our original equation? That's their y, isn't it? That d equals y equals. So that's fine. Okay, so now let's look at 2.25 times t. In this equation, let me move it up a little bit more so you can see it. Can you see it better now? Sorry about that. Okay, so this is our y, which is their d. Now we have equals 2.25t. Does that look like anything in our equations here? Yeah, it does. What does it look like? It looks like our mx. They don't have a b, but we do in our equation that we aim for. They don't have one, but that's completely fine. As long as we have some type of slope written down there, sometimes it's not always using y's and x's. In this case, they're using d's and t's, which is fine. So based on what we know now, can that be, what is it? Could it be a relationship for a linear relationship? Yeah. So I would write, I'll put it in big red letters here. Yes. Because we have our y equals mx, which is part of the equation that we use to graph and to make a table and any of that. Thank you. So, lastly, Bob. Philip, you weren't here yesterday for it, right? Do you want to try it? No? Okay, I'll let it slide today since you weren't here yesterday to start this with us. Zane. You don't think it can? Okay, why do you think that?
Because t is the time, so if you take like 100 divided by r, like let's say r was 3,
Okay.
divided by 3 would be 33.
Okay.
The r is the person's walking rate.
Okay, the R represents their walking rate, which is what they told us, and the T represents their time, which is what they stated to us below. So based on what Becky and I just went over in our y equals mx plus b form, that's the form we always aim for, that type of equation. So you don't think it is. I agree with you. I don't think it's even really written in this type of form that we aim for at all. That R is a variable right here, which is not a constant, like our x. It's not a constant. So because of that, you're right. This is not a linear relationship. You have a question?
So there's no slope.
For Bob's? Right, there's not. Any other questions as to George, Billy, Bob, or Elizabeth's walking rates and how we determine that? No? So let's look at our summary page on the back page. Here's our summary. The constant walking rate. Oh, I don't have it written down. The constant walking rate shows up in the table, the graph, and the equation. We can see that walking rate in all three forms. In the graph, it affects the steepness of the line. In the equation, it is the number multiplied by t, which is our time in this case. In the table, it is the constant change in distance as time changes by 1 second. And lastly, these are all proportional relationships. Oh, there's one more. The constant of proportionality is the walking rate. That's the last one. So you guys should all have this written down on your back page. I printed it out for you so you didn't have to write it down. And then, that's it for 1.2 notes. We do have homework, and I will write it on the board for you. We'll have the rest of the class time to do that today, and it will be due tomorrow.